Welcome back to the Deep Dive. This is the show where we dive into your critical source material to give you, really, the fastest path to being truly well-informed. Today, we're wading into one of the densest and, I think, most critical areas of modern business: how to manage complex product programs. Our focus is on turning that massive, sometimes program-killing uncertainty into predictable, disciplined execution.
It's essentially an operating manual for avoiding chaos and for defining what good looks like at every single checkpoint.
Exactly. And our source material today focuses on a very structured but also highly adaptable process. It's called the Situation-to-Method Decision Framework.
Right.
And this framework is designed to work within those typical new product introduction, or NPI gate steps. For those less familiar, we're talking about that standard progression.
You mean EVT, DVT?
Right. Engineering validation test, or EVT,
Oh, yeah.
design validation test, DVT, and then finally, NPI, or production validation test, PVT.
Wow.
So the mission here for you is clear: to get a shortcut to choosing the correct set of tools, the right methodology, based on the single biggest risk that's lurking in your program at that moment.
And what's fascinating here, I think, is the core premise. It's just incredibly disciplined. Every program faces, what, a dozen risks at the same time?
Of course.
But this whole system, it revolves around identifying the one dominant uncertainty, the one that can still kill your program, even if everything else goes perfectly well. That precise, almost ruthless diagnosis is what determines your primary operational method.
I really appreciate that focus because it just cuts through the noise of, listing every single possible risk. And for those of you reading the Scores casebook, the visual clarity is a huge learning point. They use Navy for the high-level framework, green for the go criteria, what defines readiness to pass a gate,
And red for the hard stops.
and red for the hard stops. The executive triggers that are designed to pause or even kill progression. That contrast is meant to prevent what they call schedule fantasy and unbounded scope. It forces these reality checks. Okay, let's unpack this core system because it really rests on two fundamental ingredients. You have the 7 situation types, the dominant uncertainties, and the 5 methodology families, which are our tool sets.
Right.
Let's start with the illness, so to speak, the 7 situations.
These situations are, you could say, the 7 archetypes of program failure. First up, you have design uncertainty. This is often the most common one early on. It means you've got unknown failure modes or maybe requirements that are just constantly churning because the customer or the market hasn't really stabilized the need.
Right. You haven't validated the design against its limits yet.
If you haven't, that's your risk.
And this is where engineers, I think, love to live. They want to solve that technical puzzle. But then you also have process uncertainty.
Exactly, and process uncertainty is deadly in volume production. This means the manufacturing process window, the range of temperature, time, pressure, all of that, where the product can be built successfully.
It's not characterized.
It's not fully characterized. So if you can't control your yield, this is your killer.
Then we move out of the lab
Yeah.
and kind of onto the global stage with supply uncertainty.
Oh, yeah. This is allocation issues, sudden end-of-life surprises from suppliers, or just being totally dependent on alternates that aren't even fully qualified.
If you can't get the parts, nothing else matters.
Nothing. Then there's test uncertainty. Is your test coverage any good? Does the test result you get on the factory floor actually correlate with what the customer sees in the field? And who even owns the test? Poor testing just lets defects escape.
The last 3, they feel more like program management risks. You have regulatory or customer approval uncertainty. Are we really ready for the FDA, CE marks, or that one key customer sign-off? Then there's schedule uncertainty. I see this one a lot. The critical path is unclear or buried, or you have way too many owners, which just dilutes all accountability.
And finally, cost uncertainty. This is usually yield-driven. The manufacturing scrap rate is just killing your margins, or the bill of materials. The BOM is just too expensive for the market.
Okay, that's a powerful diagnostic list. But you list 7 uncertainties. In any real-world program, aren't there usually 3 or 4 big risks happening at once? Doesn't forcing us to pick just one dominant uncertainty risk simplifying things a bit too much?
That's a fair challenge. The framework doesn't say ignore the other risks. It insists on identifying the dominant one, the one that, if you leave it unaddressed, will cause the whole program to fail, even if you solve the other 6.
Okay, so the others become secondary.
Exactly. They become secondary methodologies, but the primary method has to attack the main bottleneck. So if that's the illness, what are the medicines? That brings us to the 5 methodology families.
Let's hear the tool sets.
First up, evidence-gated execution. This is sort of like APQP Advanced Product Quality Planning. You use it when the risk is readiness or approval. You literally only proceed when the evidence package test reports regulatory sign-offs is 100% complete. No
Then you
exceptions.
have experiment-driven learning.
Right. Essential when the physics or the process window is unknown. You're talking design of experiments, DOE, deep characterization work. You run structured experiments to find the limits.
The third one sounds like you're already in trouble. Containment plus stabilization.
You are. You use this when you are already shipping or ramping. You have to prevent quality escapes immediately. So this means structured root cause analysis, like 8D or A3 problem solving, with rapid, often daily feedback loops.
And fourth, constraint-driven program management. This is your war room mode.
It's your war room mode, exactly. You use it aggressively when schedule or just coordination is the dominant risk. This isn't just about making a schedule. It's about clearing the calendar and forcing decisions daily that might otherwise take weeks.
And the last one.
Supply chain risk governance. This is specifically for volatility. It means having pre-vetted alternate components and a defined revalidation playbook ready to go.
So let's talk about that selection matrix, the matchmaking.
Yeah.
If my dominant uncertainty is design uncertainty, the matrix points me straight to experiment-driven learning as the primary method. It makes intuitive sense.
It does. You have to learn your way out of the problem.
Yep.
But if your dominant uncertainty is the schedule, your primary method is constraint-driven PM. You stop doing everything else and focus ruthlessly on that critical path.
Wait a minute. So if regulatory approval is the risk, you jump to evidence-gated execution. Why wouldn't constraint management work there? Why isn't that as effective when you are battling, say, the FDA for approval?
Because the FDA doesn't care about your schedule.
What point?
They care about your data package. You can run that constraint management war room all day long, but if the evidence required for sign-off is missing or incomplete, the regulator stops you cold. The framework forces you to use the tool that actually mitigates the root cause, the lack of verifiable evidence, not just the symptom, which is the slipping timeline. And, the real power of this framework isn't just in the diagnosis. It's in operationalizing that diagnosis with, rigid discipline. And that follows a really clear three-step decision process. First, diagnose the dominant uncertainty. Second, choose the primary and secondary methodology. And third, operationalize it.
And operationalizing it means defining the green light gate criteria and the red light hard stops.
Exactly.
Let's focus on that green light criteria for a second. What defines readiness? When you approach a major gate like DVT exit, the source material defines exactly what good looks like. It replaces that vague optimism with specific engineering proof.
And for DVT exit, there are two criteria that are just non-negotiable before you can move to volume production. The first is process window characterized and controlled. And the second is test coverage and correlation using known golden units established. Think about what that really means. You can't move forward if you don't know the limits of your manufacturing process, and you can't move forward if you don't trust your tests. These are engineering mandates, not just scheduling milestones.
And the flip side is the red light, the hard stops. These are the executive triggers designed to pause a gate or stop shipment entirely. But how often do you see leadership actually enforce a hard stop? Knowing the massive schedule impact. Does the source material talk about the politics involved?
It's very clear on this. The framework only works if there is C-suite commitment to enforce the red stop. The politics are always there, but the structure is designed to depoliticize the decision by making the criteria objective. They break the hard stops into three critical buckets. Under quality and safety, the red is a critical escape risk. That means there's a suspected latent defect, a failure mode that could exist without any validated detection or containment.
So if you can't prove you can catch it, you stop.
You stop, and that forces immediate experiment-driven learning or containment.
Okay, what about on the supply chain side?
The red there is triggered by an EOL surprise. A key component is suddenly unavailable, and you don't have a qualified alternate path ready to go. You cannot just silently swap parts in NPI to save the schedule.
And under program control, a big one is schedule sanity.
Ah, yes, hopium, as they call it. The critical path isn't mapped, dates are given without any dependency evidence. That stop is enforced by the program manager when implicit approvals and, fuzzy ownership become the norm.
That NPI program management discipline around owner clarity is so crucial. The sources emphasize one single owner per deliverable and one approver per decision. And this ties right into decision bandwidth. When you're in crisis, you need that daily triage cadence, which is constraint-driven PM.
But even normal programs need that rigorous weekly cadence for the change control board and the risk review. And the PM has to manage explicit trade-offs, deciding between schedule versus quality or cost, and documenting those agreements so the history is clear.
That decision bandwidth is often forced by what they call escalation thresholds.
Literally clock timers. For instance, if a critical task slips and there's no owner or no recovery plan, the PM has to force an executive escalation within 48 hours. If you have a suspected latent defect without validated detection, that has to lead to a stop-ship decision within 24 hours. The structure forces speed and accountability. It removes all the ambiguity about when to raise the alarm.
Okay, now let's dedicate some time to seeing these methodologies solve actual high-stakes problems, pulling directly from the casebook. The framework really shines when the stakes are highest.
Right. And the first case study takes us back to a crisis point. The frantic ramp-up of ventilators during the pandemic, case one, the Philips ventilator ramp. The situation there was clearly dual. Schedule uncertainty coupled with extreme supply uncertainty. They had to go from 500 units to 4,000 units a week.
So the method applied was a mix of constraint-driven PM, getting everyone in the war room daily, and heavy supply chain risk governance. They ran constant critical path reviews and tightened inspection for those early ramp lots because they knew the supply chain was a weak link.
And the key executive takeaway from that case was a fundamental lesson in high-speed NPI. In schedule-driven ramps, the real critical path, it often shifts entirely away from assembly time or labor. It becomes component availability and the time required for requalification of newly sourced parts.
Can you give an example?
Sure, a sudden shortage of one specific memory chip or sensor that forces you to immediately test an alternate component that instantly overrides every single labor plan you have. This framework forces you to acknowledge that shifting constraint.
Okay, let's look at another extreme example of speed. Case 2, the Plexus HEP ventilator. Here, the uncertainty was regulatory combined with test, and it was driven by a nearly impossible goal: prototype to finished product in 10 days, and with an emphasis on meeting those stringent zero defects standards for medical devices.
They deployed constraint-driven PM with an intensity few companies ever see. They ran 5 daily stand-up meetings just to manage coordination. This extreme bandwidth was paired with evidence-gated execution. That zero defects focus forced a minimum validation discipline even at that speed. They couldn't just assume quality.
So the takeaway wasn't just go faster. It was, if you accelerate the calendar from months to days, you must exponentially increase the decision bandwidth, the cadence, and the authority. Otherwise, you just risk uncontrolled shortcuts that will kill the product later.
Precisely. We also saw a really interesting situation in case 3, Plexus Zephyr Plus, where supply uncertainty became the dominant driver. It actually forced a rapid redesign of the product.
The initial components just weren't sustainable.
Right, which triggered a massive, unplanned engineering change.
So the methodology chosen was heavy: supply chain risk governance coupled with evidence-gated execution. Supply chain was tasked with securing any available material, while engineering immediately started redesigning the product around those constraints.
The core insight here is shifting to a DFSC mindset design for supply chain. When material availability drives the design, the winning move is making supply constraints a first-class design input early on, rather than treating it as a last-minute scramble that voids all your previous engineering work.
So the framework forces engineers to work within the reality of the supply chain, not just the ideal physics.
Exactly.
Okay, finally, let's look at a purely manufacturing issue. Case 4, a composite example of BGA yield instability. This plagues complex electronics. The uncertainty was process and test. You had intermittent failures, the process window wasn't locked down, and factory tests weren't correlating well with what was happening in the field.
This one required a heavy dose of experiment-driven learning paired with containment plus stabilization. They used structured design of experiments DOE across different reflow profiles and PCB characteristics to rigorously prove causality. They didn't stop production, but at the same time, they implemented 100% X-ray inspection for the affected BGAs as a strict containment action. That prevented escapes while the learning was still underway.
That distinction is so key. The executive takeaway seems to be: process uncertainty has to be treated as a learning program first, not a run harder program where you just throw more resources at an unstable process and hope the yield fixes itself.
You have to force the scientific rigor to find the process limits. If you look back across all these scenarios, the rapid ramps, the supply constraints, the technical yield issues, the framework's fundamental value becomes crystal clear. It enforces discipline over heroics. It mandates that the correct tool be used for the root cause. Whether it was hitting a cost target by gating changes with evidence or solving schedule problems with clear ownership, the structure provides predictable control. It turns reactive firefighting into planned, predictable problem solving.
So what does this all mean for you? As we've seen, knowledge is most valuable when it's understood and applied. This deep dive really shows that disciplined execution relies fundamentally on clear diagnosis. You have to stop addressing the symptoms, the slipping schedule, the rising costs, and find the dominant uncertainty that is truly driving the chaos.
Absolutely. And as a final provocative thought for you to chew on, we saw in that composite case about the dual site line transfer that schedule uncertainty often stems less from true technical difficulty and more from dependencies and, well, too many owners. So if you are facing a critical path slip this week, ask yourself honestly, is this truly a technical challenge that needs a new engineer or a redesign? Or is it an ownership problem that's just obscured by ambiguity? The solution might require implementing a simple RCI template, responsibility, accountability, consulted informed before you ever even initiate a redesign. Getting the management structure right often solves the technical problem faster than another DOE.